Cathode rays have a magnetic field. It is demonstrated with an electron gun from a Narva PR2 tube. The anode of the electron gun is supplied with 350 vac rectified but not filtered. This results in a 100 Hz pulsation of the intensity of the cathode ray and therefore of its magnetic field. A sensor consists of 12 coils of approximately 1,400 turns each. The pulsation of the magnetic field of the cathode ray induces a voltage of 17 mV in the sensor after amplification. Cathode rays do have a magnetic field. But the absence of a magnetic field in the electron beams at the exit of cyclotrons, while the electrons move at several tens of kilometers per second, shows that the motion of electrons is not the cause of magnetic fields. The one and only cause of these fields is the intrinsic magnetic field of the electrons. The measurement of the magnetic field of the electron beam of the cathode ray tube by coils shows that their intrinsic magnetic field has a rotational structure since the coils must be crossed by the magnetic field. Consequently, the magnetic field of magnets cannot be directly the result of the electron's intrinsic magnetic field. It is necessary for the electrons to be organized in toroidal structures in the material of the magnets. The electrons of the magnets, included in such structures, generate a magnetic field similar to that of the magnets. Such an arrangement could allow us to consider a quantitative explanation of the Barnett effect by precession effect. In the Barnett effect, the rotation of a magnet changes its magnetic field. The angular momentum of the toroidal structures is in their axis. These structures are put into precession. Their axis will tend to align with the axis of rotation. However, the axis of the angular momentum of these structures is also the axis of their magnetic field. This results in a modification of the magnetic field of the magnet put into rotation. The Einstein-de Haas effect was predicted by Ampere in 1820. The magnetic field of a solenoid carrying a current causes a rotation of the magnet. The magnetic field of the solenoid causes an additional alignment of the magnetic field of the toroidal structures of the magnet in the axis of the solenoid and therefore also of their angular momentum in this axis, which is also the axis of the magnet. This results in a rotation of the magnet by this angular momentum. A conductive disk is placed in the magnetic field of a magnet. A brush collects the current at the periphery of the disk. When the magnet rotates while the conductive disk is stationary, no current is detected in the disk. Even if the magnetic field of the magnet is increased by its rotation according to the Barnett effect, the fact remains that all the field lines are identical. Nothing therefore is changed for the electrons. On the contrary, if the conductive disk rotates, it is crossed by a current. No current should be expected, since the magnetic field and the surface of the circuit remain unchanged. Faraday's law relates to a variable flux of the magnetic field through a given surface of the conductive circuit. Relativists have given an explanation based on reference frames. The speed involved in the Lorentz force would be relative to the reference frame in which the measurements are made, therefore in the laboratory. They therefore claim that there would be a movement of electrons in a magnetic field and therefore a Lorentz force perpendicular to the field lines and to the tangential speed of the disk. The resulting radial current would be collected by the brush. Why would this current not exist when the magnet rotates? Wouldn't the movement be relative? Wouldn't the speed of the magnet belong to the same reference frame? This explanation by mathematicians takes no account of the fact that electric charges have an angular moment. In reality, when the conductor rotates, the angular moments of the electric charges statistically align in the axis of rotation by precession. The intrinsic rotational magnetic field of the electrons behaves like that of a current line. The current lines attract each other. But since the number of electrons is higher at the periphery than at the center, the electrons are attracted to the periphery. The excess electrons are collected by the brush. Rowland's experiment is usually presented in a simplistic way by a compass deflected by an electrically charged rotating disk. The reality is much more complex. A magnetic field is only observed near the edge of the disk as seen in this photograph. Rowland used a kind of circular capacitor. A rotating, positively charged conductive disk was placed between the negative plates of the capacitor. Two compasses are suspended from a wire. The bottom one is placed at the edge of the rotating disk. The small deviation resulting from the magnetic field is detected by a mirror attached to the wire. The rotational magnetic field is the integral of the fields of the turns traveled from the axis of the disk to the edge. It is therefore maximum at the edge of the disk. In Maxwell's theory, this rotational magnetic field has a component in the plane of the disk if it is measured above the disk, or in a plane perpendicular to the disk if it is measured on the edge of the disk. Maxwell's theory takes no account of the fact that electric charges have angular momentum. In reality, when the disk rotates, the angular momentum of the electric charges statistically aligns with the axis of rotation by precession. And so the orientation of their magnetic field changes as it is linked to their angular momentum. It is precisely this orientation that is the cause of the magnetic field of the Rowland disk.